Hello, everyone. Thank you very much for joining us today. I'm going to hand the stream over to Professor Impey, and we're going to get started with questions.
Okay, welcome everyone to another live session for the online classes, and the floor is open for your questions.
So the first question for today is going to be from a live viewer who would like to know about a NASA mission. So NASA is launching the Dragonfly mission to study prebiotic chemistry on Titan. Can you tell us more about the mission and what is currently the state of the art of prebiotic chemistry?
Yes, Dragonfly is a very exciting concept. NASA has ambitions to study the outer solar system as well as Mars, which is a go-to target in the inner solar system. The Dragonfly mission is aimed at Titan, a very exciting moon of Saturn, which has a thick nitrogen atmosphere, which has large bodies of liquid ethane and methane. It's too cold for liquid water to be there, although there's a little water probably mixed in with that fluid. And this is a world that has, has deep bodies of liquid. It has probably complex hydrocarbons. It has weather. It has clouds. It has erosion. It has rivers on its surface. It's a fascinating world. And NASA has sort of booted into 21st century technology because the Dragonfly is essentially a drone technology. And so you can get a sophisticated instrument package in a small mission. And with a drone, you can hop around the surface or with buoyant flotation devices, sample the liquids in these shallow bodies of ethane and methane. And that's what Dragonfly is intended to do. It has to work fairly autonomously and robotically because Saturn, of course, is so far away that it takes signals a good fraction of an hour to get there. So there's no real-time control. You can't imagine someone with a joystick running this drone the way you would run a drone in your backyard. So it's a different kind of concept, but it's very flexible. It's very powerful. It takes advantage of state-of-the-art technology on the Earth. It's going to be a decade before this mission is working. And then as far as what it expects to find and what the state of our knowledge of prebiotic chemistry is, really we don't know a lot. We haven't filled in the gaps in how simple chemicals on the Earth got together to form the first cell, almost certainly within the first few 100 million years after the Earth formed. And on Titan, the chemistry is going to be so different that we really have no expectations. I mean, people don't know what to expect. It's alien chemistry. It's probably not going to be informative of how life started on the Earth because it is so different. But synthetic chemists and computer models suggest that if you have a mixture of ethane, methane, a little water, and ammonia, and other solvents, other dissolved solids in that liquid, you can form fairly complex molecules naturally. It's not clear that you would get the basic building blocks of terrestrial life. You might get something entirely different, and it might be biological in a different way. So it's a very exciting mission, probably the most exciting one that NASA is contemplating.
The next question is from Hussam, who's on with us live, who would like to know if you can please talk about the level that telescopes have reached in the face of barriers caused by the Earth in giving us more accurate data on the universe. So what are some of the barriers? How have we overcome barriers? And what are some upcoming barriers for telescopes?
So as you make all modern telescopes, optical telescopes now I'm talking about, and near infrared, are reflectors. So refractors were the original telescopes of Galileo, and they went up in size to the Yerkes Observatory, which is about a meter refractor, i.e. a telescope with a lens. And then it became clear that to do much bigger light gathering, you needed thin mirrors. So as telescopes move up to 8 and 10 meters in diameter and beyond, the limitations on these telescopes there's a couple. The first is just mechanical. It's hard to make a telescope of that size, which is able to collect light and focus it extremely accurately. Remember, to make a sharp an image as your optics would allow, you actually have to have a mirror surface that's precise to around the wavelength of light. That's a very tiny number. So these are extremely precise mirrors. And since they'll sag mechanically, all the large telescopes have active optics. This is a combination of actuators behind the primary mirror that keep it in its shape as it moves around the sky and flexes differently due to mechanical stresses. And more importantly, a secondary mirror above the telescope that is the final reflection before it comes to a focus. And that somewhat smaller mirror, for a 10-meter mirror, 10-meter primary mirror, the secondary might be a meter across. That is very thin shell that is highly adaptable by actuators, very fast, dozens of times a second. It's essentially correcting not only the imperfections in the telescope surface, but also the fluctuations in the Earth's atmosphere. So the second limitation beyond the mechanics of the telescope is the Earth's atmosphere, which blurs light coming in compared to a space mission. And these adaptive optics on the secondary mirrors of large telescopes are getting pretty good at taking out most of the distortions of the Earth's atmosphere. So that's been very successful, and it's allowed people to contemplate mirrors or telescopes 20 to 30 meters across, which is the upcoming generation of huge telescopes. A final limitation that can't be overcome by technology is the fact that the Earth's atmosphere is opaque in certain wavelengths. It really only admits visible light between about 350 nanometers, and then there's through to a micron, and then there are a few other windows in the near infrared, 2, 3, 5 microns. So otherwise, it's opaque, and there's nothing you can do about that. That's the water vapor and other molecules in the Earth's atmosphere. So for certain wavelengths of astronomy, you just have to go into space, and there's no way around it. But given the limitations, telescopes continue to get bigger, and they continue to get more powerful.
Thank you very much. The next question is from Alexis Frey, who's on with us live, who would like to know, could a perfectly stable planetary system just like ours form around a black hole, or would the radiation from the black hole somehow disrupt the planet formation process?
So planetary system around a black hole is essentially very unlikely, because a black hole is the remnant after a massive star dies. And a massive star will die as a supernova, so cataclysmic explosion. So the planets would have to have pre-existed the formation of a black hole. You could certainly have a massive star which has a planetary system around it, but it is not at all clear that that planetary system would survive the supernova event and therefore still be around when the black hole exists. Now, people were fairly confident of the absence of planets and Earth-like solar systems around dead star remnants, and except for the fact that the very first exoplanets found in 1992, so they preceded the discovery of 51 Peg, the famous discovery that got a Nobel Prize a few years ago, were found around pulsar. And a pulsar is another stellar remnant akin to a black hole that is left behind when a star dies as a supernova. So it is apparently possible for planets to exist around the stellar collapsed remnants, and it's not clear how they form. It's possible that the rocky material in the pulsar planet case was accreted after the star died. It didn't form when the star was born a long time earlier. We simply don't know. So models still suggest it's hard to get planets around stellar remnants, but we do have these pulsar planets to explain, and it actually is a puzzle in planet formation.
All right, thank you very much. The next question is from an email from Anthony, who would like to know if it is possible that asteroid 99942 Apophis could hit the Earth when it makes a close pass in the year 2029.
Right. So this asteroid is one that astronomers have been looking at for a while. It's on an orbit, and it's a highly elongated orbit that occasionally passes fairly close to the Earth. And there is a configuration which is called a keyhole, where it can go through an orbital trajectory which puts it gives it a high probability of colliding with the Earth. And there's been some speculation that the close passage in 2029 will be such a keyhole event, leading to a substantially enhanced probability of an impact. Remember that in general, even for a near-Earth asteroid or an Earth-crossing asteroid, the odds of an actual collision are tiny because space is so big, and even if the asteroid is coming relatively near us, the odds of a collision just end up being very, very, very tiny. Apophis is an exception to that, where in the calculation of the trajectories, the probability becomes finite. That's not to say it becomes large, like 90% likely or 50% likely, but even at the level of a few percent, that's a serious concern. So I think at the moment, we simply don't know the orbit well enough to be more precise. Typically what happens is when you have better orbital data on one of these asteroids or near-Earth objects, you calculate a better trajectory, and the more precise trajectory shows that it in fact will miss the Earth. And so the allowance, or the fact that it might hit the Earth, is sort of a function of poor data rather than any actual likelihood that it'll hit the Earth. And that's a little bit the case with Apophis. So between now and 2029, obviously there's plenty of time to get better orbital data, and we'll be able to figure out whether it's a true danger or not.
Thank you very much. The next question is from a live viewer, Space Time with Robert. We'd like to know, since the expansion of the universe has slowed down enough for light to reach other galaxies, how long has a distant galaxy like Malin 1 been observable from within our own Milky Way galaxy?
So the universe was slowing down in its expansion rate for the first roughly 7 or 8 billion years. Since then, in the last 4 or 5 billion years, dark energy has made the expansion rate increase. So during that time, that good chunk of the early history of the universe, when it was decelerating, light could reach us, of course, from more and more distant objects. The galaxy that you ask about, Malin 1, an object I've studied myself because it's a huge low surface brightness disk galaxy, is at a pretty low redshift. It's a redshift of 0.1. So that's actually not very far away in a cosmic sense. So Malin 1 is not moving away from us with a very high velocity compared to the speed of light. So its light has essentially been visible to us for the entire history of the Milky Way galaxy.
Thank you very much. The next question is from WS, who's on with us live, who would like to know, is there a fundamental unit or measure of time that would have relevance to the entire universe? Can we somehow measure time from space itself rather than just our planet's relative motion through it?
The natural unit of time, time, of course, is measured in human units, seconds, minutes, hours, years, months. These are just human measures of timekeeping. The fundamental units of time in the metric system are reference to oscillations of cesium atoms or some fundamental particle, some fundamental atom oscillation, where, of course, a second or a human unit of time is an enormous number of these oscillations. So most human units of time are completely arbitrary in terms of physics. The natural one in terms of cosmology, of course, is a gigayear or a billion years, because that's, in round numbers, it's the order of magnitude of the age of the Earth. The universe is 10 or so times larger than this number, and so it's a natural unit for thinking about cosmological observations. But time as a measured entity is, in the end, has to be referenced to subatomic properties, because the only things we know of where the timekeeping is precise involve the either the radioactive decay of heavy elements or the oscillations, nuclear oscillations or harmonic oscillations of individual atoms. And so we reference time on Earth to that, and if we move beyond Earth or other civilizations had worried about timekeeping elsewhere, they would probably do the same thing.
All right, the next question is from a live viewer, Laurentiu, would like to know, what is the latest status of research on dark matter? Is there any clue on it, or and what are the ongoing activities in the field?
Dark matter is an active subject of investigation. It's sort of two-pronged. The astronomers are continuing to measure dark matter on different scales and try and understand its properties. Now, that's very difficult because dark matter is essentially has been sculpting cosmic structure on large scales. So we can diagnose the existence of dark matter, but it's very hard to say what it's fundamentally made of. So in astronomy, the most useful situations are cases like clusters of galaxies or clusters in collision, like the Bullet cluster some years back, where we can see a little astrophysical experiment that gives us some hints as to the nature of dark matter, its fundamental properties. There are not many of those experiments, and I would say that field has not progressed very far in the last few years. The fundamental physics of looking for the dark matter particle is progressing because there are a dozen or more cutting-edge experiments to look for dark matter particles, which are presumed to be supersymmetric extensions to the standard model of particle physics, or possibly axions or other exotic particles that are not part of standard physics, but they are part of extended physics or new idea physics based on supersymmetry theories, for example. Those experiments have not succeeded so far. People continue to upgrade the experiments, larger solid mass detectors, liquid detectors, down mines, and so on. And because the interactions of dark matter with normal matter are so weak, because it has no electromagnetic interactions, it's typically a resonance or a mechanical reaction in the detector, you need huge detector volumes and large amounts of time to gather enough signal to look for the very rare dark matter interactions. So none has succeeded. There's probably 5 or 6 of these experiments which, if they fail in the next few years, actually will make a crisis for dark matter physics, because we'll have ruled out some of the most plausible candidates and be left with not much to guide us in terms of what dark matter is. So people have a sense of anticipation that the dark matter particle may be discovered in a physics experiment, because if it isn't, we're kind of, all bets are off and we're kind of in trouble.
The next question is from a live viewer. Pecornin would like to know, why is it that merging black holes lose energy?
Well, merging black holes lose energy because they're, if you think about it, when merging black holes come together, they have 2 forms of energy beyond their mass energy. They have kinetic energy because they're obviously traveling at some significantly high speed, could be a significant fraction of the speed of light. And they also clearly have rotational energy. They have orbital energy, depending on the way they move around each other as they coalesce. And they have angular momentum or spin energy. And so when black holes merge and coalesce, some combination, depending on the initial conditions of the system that with the 2 components that merge, some fraction of the orbital kinetic and angular momentum energy of the individual objects is released when the system combines. And that a lot of that energy comes out as gravitational waves or gravitational radiation, which is, of course, how we detect these merging black holes.
Thank you very much. The next question is from an email. Tony Lynn would like to know, if relativistic speed were technically possible, what would be the expected adverse physiological consequences of accelerating up to that speed or traveling at that speed?
Well, if humans or big objects, as opposed to subatomic particles, could be accelerated to relativistic speeds, I suppose one possible problem would be the acceleration itself. I mean, if you've ever, most people have never been even in a racing car, for example, but the acceleration of a drag racing car or some car that has extreme acceleration is sufficient sometimes to even break bones in a human body. So if you're in a rocket or some conveyance that is accelerating towards the speed of light, unless it's going to take a very long time to do it, you're going to be subject to pretty significant g-forces. So that's an obvious issue, is how long is it going to take to accelerate to near light speed and avoid g-forces that would, kill you. Once you get to relativistic speed, there's no intrinsic problem with traveling at that speed. If the spacecraft or the object you're traveling in is secure, you are in a relativistic situation. So as seen by an outside observer, you're going to be compressed in the direction of motion, physically actually compressed. And as seen by the outside observer, your clocks will start to run slowly as according to special relativity. If you have been paying attention or comparing the clock or the watch you have on your wrist to an atomic clock that's with you in the spacecraft, you won't notice anything strange. It doesn't seem like anything's wrong, and you clearly don't think that your body is being compressed, and you don't feel that. So these strange effects of special relativity would only be seen to an outside observer. So interestingly, you would really see nothing particular going on as you travel at these very high speeds.
Thank you very much. The next question is from Ubar, who's on with us live, or Ubar, who's on with us live, who would like to know, I was wondering how we knew where to look and when to capture the image of the active black hole.
I'm not sure which black hole is referring to, if it's M87 one, the event horizon of last year.
Yes, I believe it's that one. It's the one that was recently released.
So that's been on astronomers. M87, active galaxy M87, is a distance of about 60 million light years, one of the Messier objects, so it's a very bright galaxy, almost visible to the naked eye. That object has been on astronomers' radar for a long time. Because, as we see, it's one of the Messier objects, so it is one of the brightest nearby galaxies in the sky. It's the most massive galaxy, bright galaxy in the nearby universe. It's a giant elliptical galaxy with a mass that well exceeds 1 trillion solar masses. And it's been known since the 1950s, actually, to have an active core. So optical images taken a long time ago showed an optical jet or bright nucleus. And radio images, when radio telescopes matured in the 60s and 70s, showed a radio jet. So it's been known to be an active galaxy for decades. It's been well studied, and because it's nearby, you have good angular resolution. So telescopes like Hubble can take incredible pictures of it. And so very quickly, as people got to the point of doing the Event Horizon Telescope experiment, put it on their target list. It essentially vied for supremacy as the best first target for the Event Horizon Telescope with our own galactic center. And I think our own galactic center's black hole is the second image you're going to see a press release for sometime this year. But M87 was a bigger, splashier black hole. It's 6 billion times the mass of the sun. And so it, having been, again, well known to astronomers as an interesting active galaxy for decades, it was almost a natural choice for that first image and that spectacular result from last year.
Next question is from a live viewer, Jammy Pants, who says, "Hi, Professor. I loved Einstein's monsters. My question is with regard to Type 1a supernova events. Are the resulting shock waves moving at near relativistic speed, and why or why not? And then how does this relate to potential Betelgeuse explosion?"
So yes, supernova type 1 or type 2, the supernova type 1As are binary systems where the companion just gets enough mass to push it over the Chandrasekhar limit, and it does a core collapse and a supernova explosion of pretty fixed luminosity. When the core collapses, it bounces. It essentially meets material coming out from the core that's already fallen in, and that collision between the material on its way out and the material falling in, both at significant fractions of the speed of light, creates phenomenal temperatures, billions of Kelvin, momentarily for a very short period of time. And that's the blast wave. That's the explosive nucleosynthesis, as it's called, that generates the burst of heavy elements from a supernova. So this is a relativistic core collapse and a relativistic explosion. And the amount of energy involved is simply phenomenal. It rivals the energy of an entire galaxy. So that's what supernovae are, and either kind are very interesting, of course. And we understand the physics of them pretty well because supercomputers have now been able to model them quite well.
All right, the next question is from They Call Me TJ, who's on with us live. Who asks, in a previous live session, you said that the sun has a 22-year cycle of sunspot activity, but other literature says it's an 11-year cycle. Can you clarify or talk more about that?
Mm-hmm. Yeah, so the sunspot cycle is the cycle from maximum to minimum, and then the next maximum is indeed 11 years. But what happens at the sunspot minimum is that the magnetic field of the sun winds up and then tangles and essentially disappears, and the sun's magnetic field flips. So each of the 11 years represents a magnetic field in a different direction. So the full solar cycle represents when the magnetic field of the sun goes back to the orientation it had a cycle before, and that's 22 years. So the sunspot cycle is essentially half the length of the full magnetic field cycle.
Well, thank you for that clarification. Again, Gail Roberts, who's on with us live, references a previous question and answer session where she noticed a sign on your wall that says "No weapons in space." How confident are you that this will remain the case? Is there an international agreement about this?
Yes, well, it's well spotted. Yes, there is actually. So the Outer Space Treaty of 1965, early in the history of the space program, Sputnik was 1957, so this was within the first decade before we went to the moon during the sort of Gemini and early Apollo years. The Outer Space Treaty of 1965 very clearly had the goal of not allowing the major powers, world powers, to put weapons in space. It was designed to avoid nuclearization of space. It was indeed signed by most of the world's powers. I think it's been signed by well over 100 countries, and I think maybe only 4 countries have not signed it since then, and there are some sort of rogue states that you almost might expect, like North Korea and Iran, and I'm not sure of the other 2, but they're not. Well, North Korea has nuclear weapons, so that's obviously a concern. I think only one of the non-signatories is a nuclear power. But the main nuclear powers of China, Russia, and the US have signed it. And so it's been a reassurance for that period of time that nukes will not end up in space. But people have lost confidence for 2 reasons. One is that enforcing something like that's a UN treaty, of course, so it has the power of the UN and the Security Council behind it. But enforcing that is really difficult. How do you enforce it? How do you monitor all the hundreds and hundreds of satellites that get launched every year to know what's inside them? Because nuclear warheads can be highly miniaturized now. I mean, not super miniaturized, but they can fit inside something the size of a soccer ball. So it's really hard to be sure of everything that size and what it is. And the second is China's ambitions in space are large. They're going to have a space station in a year or so. They have very active and aggressive plans to go to the moon and Mars and have bases eventually on both places, as does the United States, but actually with a longer time scale. And in China, there's a lot of secrecy of their space program because it operates hand in glove with the military-industrial complex. So American commentators and other neutral observers are quite anxious that it might be possible for the Chinese to nuclearize space. And people got very nervous when China blew up one of its own satellites and caused a lot of space debris. That was a highly antisocial act for world spacefaring power to do. So that's probably the big anxiety right now.
The next question is from Koyum Alelu, who sent an email. And the question is, we know all planets except Venus rotate in the same direction, and we also know that the mass and energy of the sun brings about warps in space-time. So what is it that makes Venus rotate clockwise while the others rotate anti-clockwise, and does it have to do with the general theory of relativity?
Yeah, it's an interesting question. Yeah, Venus is an exception. It counter-rotates. So the sense of the rotation of the planets makes sense in terms of angular momentum, because all the planets except Venus and really Uranus, which is tilted on its side, but let's just set that aside for a minute, spin on their axes in the same sense that they orbit the sun, which means the angular momentum vectors are aligned between the planet spin and the overall angular momentum of the solar system. And that makes sense when you form an object from a collapsing gas cloud. Venus's counter-rotation makes no sense. And so astronomers essentially, or physicists, essentially deduce that that cannot have been the initial condition, that cannot have been how it formed, and some catastrophic event must have caused Venus to counter-rotate. And the obvious reason would be a collision with a very large object early in the history of the solar system, before the planets had fully formed and before their orbits had stabilized. You can conjure up, if you make computer simulation, you can conjure up a collision that could have done that to Venus and still in the end left it in a fairly stable orbit, just as you can conjure up circumstances whereby a Mars-sized object hit the early Earth and splashed off the moon. So we know that such large impacts did happen very early in the history of the solar system. Unfortunately, there's no smoking gun. There's no way, after 4.5 billion years, there's nothing that we can see. Well, we can't see Venus anyway. It's cloud shrouded, but then we have very little information about the planet for that reason. There's nothing we can do to prove that that happened, because obviously the impactor has long since gone, and evidence of its impact has been obliterated, in Venus's case, of course, by volcanism. So it's just a hypothesis, but it seems a reasonable one.
The next question is from a live viewer, Ram Krish, who would like to know about Betelgeuse. So several people are interested in the current status of Betelgeuse, but this one specifically is says, we're noticing that Betelgeuse is in some kind of minimum in its cycle, so its brightness is dimming. Is that correct? Is it some kind of variable star? So what is causing the dimming, and what is the current status?
Yeah, it started to show dimming episodes, and also more recently, some high-resolution images have shown that it's no longer symmetric. Its image is not symmetric. Now, astronomers can't really make a detailed map of Betelgeuse. It's a star at some significant distance from the Earth, and astronomers can't really resolve stars. They're still points of light for the most part. But high-resolution imaging does show that it's non-circular at the moment, and that's not clear. It's not clear whether that's a truly non-circular shape of Betelgeuse, or whether the emission from Betelgeuse has become non-uniform, and so giving that impression. Either way, Betelgeuse is undergoing some serious changes, and with stars, in the end of their life or any time in their life, the only reason for such dramatic physical changes is a change in the energy source at the center. So the nuclear fueling, the fusion fuel that keeps the star puffed up, that causes the light to get out, diffuse out, and then travel through space, has been interrupted or is changing. And that's, of course, what's leading to the speculation that it's nearing the end of its life, because as a massive star nears the end of its life, it runs out of hydrogen initially, and then it goes through a crescendo of nuclear burning phases or nuclear fusion phases, ascending through the nuclear fuels towards iron, the most stable element. And if indeed Betelgeuse is starting to do that, then the end is near, and because at the end of that process, the core collapses and you have a supernova. There's no way to tell if Betelgeuse is really near that phase, and even some of the late phases when heavier fuels are being fused than hydrogen to helium, they still can take hundreds of years or tens of years, those phases. So it doesn't mean that it's just around the corner. Essentially, astronomers are learning more about the situation as they observe it. It's not a situation familiar enough that people are able to directly predict what's going to happen from one week to the next.
All right, the next question is from Lawrence K., who's on with us live. If there was an asymmetry of matter and antimatter at the time of the Big Bang, is there an explanation or theory underlying this asymmetry? Could there be another universe composed of antimatter?
So the hypothesis of an asymmetry fits the fact that we live in a universe with an enormous amount of matter, 10 to the power 80 particles, mostly protons, an equal number of electrons and neutrinos and much lighter particles, and no antimatter. So antimatter is essentially absent. So telescope observations have convincingly shown that there are no anti-stars or anti-galaxies. So on all scales we can look at, gamma ray limits are very strong, because wherever matter and antimatter would meet or rub up against each other, you get a lot of gamma rays, and we can sensitively rule that out. So we know that we live in a matter universe, not an antimatter universe, but we also live in a universe where there are hundreds of million, several hundred million photons for every particle. So we live in a universe that's made of radiation rather than matter. And so the hypothesis in physics is that some slight asymmetry by about 1 part in 100 million or a few hundred million early in the universe between matter and antimatter, essentially a very slight excess of matter over antimatter, played out when normal particles formed, and so electrons and positrons annihilated for the last time. That slight imbalance gave a large amount of radiation and the tiny residue of matter, and then when quarks and antiquarks annihilated, that very slight excess of normal quarks gave the matter content of the universe and a large amount of radiation from the annihilation. So that's the scenario. Now, the explanation for the scenario, or the physics behind it, is less clear. There are unified theories of physics, supersymmetry theories, and so on, related theories, which can postulate a slight asymmetry in nature between matter and antimatter, which is otherwise perfect. I mean, in the lab, a lab physicist will be very hard-pressed to demonstrate any asymmetry between matter and antimatter. But at a very fundamental level, there might be one that arises from grand unified theories. And so that's what people are stretching for as an explanation for the way the universe is. Now, how do we test those theories to see if that's, is that just a just so story, to use the Rudyard Kipling reference, or is it a true physical explanation? It's really hard to tell. We'd have to show that these supersymmetry theories were valid. And physicists have been unable to do that. Particle accelerators do not have sufficient energy, and physics experiments are not clever enough and can't access high enough energies to show that these theories are correct. So at the moment, we have plausible explanations for how the universe got to be the way it is, and they're not really well tested.
Thank you very much. The next question is from Achim, who is on with us live, who would like to know, beyond what we talked about earlier, what is your take on the future of telescopes? This person read about research at Harvard that said tomorrow's telescopes will be planet-sized quantum teleportation devices. What are your thoughts?
Right. Well, planet-sized quantum teleportation devices, that's quite an amazing thought. But the question of what is the limit of telescopes, that's an interesting question, because we're currently in a phase of trying to construct 20 to 30 meter telescopes, having had a burst of building 8 to 10 meter telescopes. And that was a wonderful period of time, because before that we only had 4 and 5 meter telescopes. So it's been going very well. There are some engineers and some physicists and scientists who think that it's going to be hard to go much beyond the 30 to 40 meter class of telescope with current technologies. I think that's probably true because of mechanical reasons, just that once you scale a telescope up, in physics in terms of cost especially, the cost of telescopes historically has gone as the 2.5 power of the aperture. And that's so that makes sense, somewhere between going up as the area and the volume. And that makes sense because a telescope has to be in a structure, right? So even though the mirror is a 2-dimensional surface, essentially, it's in a 3-dimensional building that has to contain it and protect it. And that's expensive. As the building gets bigger, it gets more expensive. So there are limitations of cost, limitations of mechanical engineering. And I think to go beyond that to the 50, 100 meter and greater class, you have to go into space, where gravity is not an issue. And since you can't carry big physical objects into space or launch them, and these things will have to be thin mirrors, very thin, they'll break. It's a situation where we're going to be fabricating these things in space. So we're going to be 3D printing super thin mylar type layers that we somehow make rigid and mosaic together into a super large dish, and use a little fleet of rockets or retros attached to it to sort of keep it in shape, or perhaps not a single physical object, but it's a fleet formation of 10 or 50 meter size mirrors that are going together to make a 1,000-meter mirror or something like that. So there are various concepts like that of doing this in space, where the challenge is to get the hardware into space and fabricate it. But once you're there, the environment is a little more forgiving than the Earth, with weather and gravity and mechanical stresses. So those are the designs and ideas I've seen. I would say none of those, even the test technologies in orbit, are 5 to 8 years away. Building something that size, like 50 to 100 meters in space, is decades away. It's probably 3 or 4 decades away. So it's going to be hard to get to the next level of telescopes.
All right, the next question is from Ranjan, who's on with us live, who asks, humans have tried to relate cosmic phenomena to their own lives and well-being since the Stone Age and probably before. Why is it that you think we do this?
Well, the lure of astronomy is built into humans because, and historically that's because humans have been coupled to the pattern and the cycles of the night sky. So you don't need to look very far to understand why early humans cared about astronomy, because they didn't live in cities. There was also no light pollution, so they were very familiar with the sky, very familiar with the cycles of the sky. And those cycles of the sky, the daytime sky with the sun and the moon, and the nighttime sky with the stars, were essential for them to keep time, to navigate and find food sources, move around the planet. And of course, they had a cultural purpose because they became useful for storytelling and myths and legends, because this is hard as it is to imagine before the age of the internet or TV or mass media. So the sky had a multi-purpose function for early civilizations, and they were innately familiar with the cycle of the seasons, the night and day cycle, of course, but also the seasonal cycle, and even some more subtle cycles. The Babylonians, for example, made good enough observations to see the precession of the equinoxes, which takes millennia to happen. So, and they could see precession of other subtle signals in space. So this has been with us for a very long period of time. And then, of course, it connects to another issue, which is just pure curiosity. Just using the cycles of the sky to regulate your life and run agriculture is one thing, but humans have fairly substantial brains, and they're curious. And so everyone from the days before agriculture, nomadic hunter-gatherers, were, I'm sure, wondering, what are these lights in the sky? What are these objects? What are these transient events like supernovae and these meteor showers that they could see? I mean, intense curiosity. And, you know, at some point, telling myths and legends to go with them isn't sufficient. And so science is invented by the ancient Greeks, and you start to have natural explanations for these events that people have been familiar with for millennia. So it's a very organic thing, astronomy. It's very built into humans and how they function and how they think about their larger world.
Thank you very much. Next question is from Will, who's on with us live, who says, there is now a controversy regarding the Hubble constant. If that led to the discrediting of the Big Bang theory, what would be the implications?
Yeah, that would be a big deal. So the question alludes to something that is legitimate now. Some astronomers just hoped it would go away and just be a storm in a teacup. But it is emerging that the local measurement of the expansion rate of the universe, which is the Hubble constant, that's the classic Hubble constant measured by observations of redshifts and distance of nearby galaxies, as was done by Edwin Hubble in 1930, that measurement of an expansion rate in the local universe is not consistent with the expansion rate measured at much larger distances using direct methods such as gravitational lensing. And also there are things associated with the microwave background. So there's this disconnect, there's this discord between what are called local measurements of the expansion rate, or the Hubble constant, nearby universe, galaxies tens of millions of light years away, and distant measures of the Hubble constant, so redshifts of a few tenths or a few, and distances of billions of light years rather than tens of millions. And the level of the disconnect in recent papers is, in astronomers' statistical terms, 5 sigma. Now, 5 sigma, as a fluctuation, if you think you understand your sources of noise, is a very, very rare thing to happen. It will happen less than 1 in a million times. So unless astronomers have underestimated their errors or missed some very profound and significant systematic error, then this is a real issue. And there's no simple way to reconcile it. It means something fundamental in the model, the world model, which is our model of the expansion, the cosmic expansion over time, which involves, of course, dark energy and dark matter, is wrong, is flawed. So reconciling this discrepancy is a very important thing in cosmology. It's risen to the top of concern. And the field is really divided as to whether there's just an unrecognized error in one or more of the measurements and it's all going to go away, or whether there's a huge fly in the ointment enough that we have to retool our underlying cosmological model. I'm sort of agnostic on this because I could see reasons for both. It could be interesting to have to need a new cosmology, but the history of astronomy suggests that often you have errors you didn't recognize or understand. So that'd be a more mundane and more historically frequent occurrence if that were the case.
All right. The next question is from Dennis Baller, who's on with us live, who has a follow-up to your Firefly mission discussion. When will the Titan mission start, and when will the probe arrive at Titan?
So unfortunately, I'm not going to pull that number out of my head because I can't remember it. The mission design is fairly stable. It's in NASA's budget, its funding budget stream for the next 5 to 10 years. I'm going to guess it's aboard 10 years before that mission is on its way, and it takes several years to get there. So getting the science out of that is probably 12 or 13 years, but don't hold me to that because I just don't remember the exact number. But these are outer solar system missions are difficult, complicated, and long. They take typically a decade or so.
And then I just Googled it real quickly, and the NASA site says that it will launch in 2026 and arrive in 2034. So.
Okay, yeah.
The next question is from Tanmay Tarkar, who is on with us live, who has a more open-ended question. What is the one thing about the universe that tingles your mind the most?
I think it's a good question. The thing that provokes me the most is whether or not the multiverse idea is correct, whether or not the quantum origin of the universe was from a context where there are other space-times that we haven't yet been able to inspect or understand, because that just opens the box of cosmology out outrageously. I mean, the universe is already huge and has hundreds of billions of galaxies, but if our entire space-time is just one part of an even larger construct, then that's sort of mind-blowing, literally and metaphorically. So that's probably what tickles me the most, and it would be fun to find out the answer. Astronomers are, trying to reach for ways of showing whether that concept has any validity, and they haven't found any yet, but they're still working on it.
All right, and I think we have time for one final question from DevWriter, who would like to know, there are spiral galaxies that were discovered to exist without the effects of dark matter. Is that true, and what are the explanations for that?
There are a couple of instances of spiral galaxies that do not seem to be embedded in substantial or dark matter halos of the size of the dark matter halo of the Milky Way, for example. So dark matter statistically in the universe outweighs normal matter by a factor of 6. So true of the Milky Way, it's true of all the large galaxies we've studied. So when you find a galaxy that is light in dark matter or has none, I don't think there are any that really have none, but there are certainly some that have very little compared to the Milky Way or their size. That's definitely a strange situation. It's very hard to imagine how they formed that way, because essentially the normal matter in a galaxy condenses within a dark matter halo, and you need the dark matter halo to get the normal matter to collapse, lose energy, form stars, and then settle into a stellar system. If that doesn't happen, we really don't understand galaxies at all. So in these cases of supposedly spiral galaxies with no dark matter, astronomers are hoping or reaching for the idea that it happened subsequent to their formation, that perhaps there was a collision, a stripping event where the dark matter, where the normal matter of two galaxies, say, collided, because the normal matter is viscous, and so when it collides, that matter will mix and sort of slosh together and stick, whereas the dark matter essentially doesn't see the other dark matter except by gravity, so it'll pass through. The dark matter halos of two galaxies will pass through each other with some substantial distortions, but without a collision directly. So you can arrange scenarios where a galaxy gets stripped of its dark matter because of some set of interactions and collisions, but it turns out they're quite artificial. They're sort of hard to arrange. So I would say those observations, the questions alluding to, are really interesting, and they may be telling us something fundamental about dark matter itself, rather than the fact that, you know, this galaxy had a very particular history. It's more interesting if they could give us a clue into the nature of dark matter, since we don't know what it is. Well, thanks very much for your questions. They were all over the map and interesting as always, and we'll be back with you in a couple of weeks.